Hello everyone, I'm very happy to join the second season of geometric analysis, past, present, and future. Thanks for the organization's invitation. Today, my title is Quantitative Rigidity for Constant Mean Curvature Surfaces in Three-Dimensional Euclidean Space. For constant mean curvature space in Euclidean space, the classical rigidity by example says any smooth boundary of domains in three-dimensional Euclidean space with constant mean curvature must be a round sphere. And today our goal is to get a quantitative version of this rigidity theory. More precisely, our main question is if a boundary has a mean curvature almost equal to a constant, then this sigma is close to a round sphere. There are many known results on this topic. If in the convexity assumption, under the convexity assumption, there are many known results by Discant, Moore, Schneider, and Arnold. But under the non-convex setting, there are some counterexamples. More precisely, there are two spheres gluing by a small cateloid leg with mean curvature close to a constant equals to 2, but the geometric shape of this surface is close to touched sphere with the same radius. For this phenomenon, we call it collapsing. But these years, there are also many results in the non-convex setting, which in the non-convex setting, most of the known results are in some supercritical case, which means the mean curvature of the surfaces is close to a constant in the C0 sense, which called the delta 0 omega. For H0, we mean n times the volume of the boundary of the domain over n plus 1 times the volume of the domain itself. For round sphere, this quantity just equal to n, which is exactly the mean curvature of the sphere of the round sphere, round ball. So here we got this constant H0 to be a replacement of the average of the mean curvature, but it only involves lower order information, which means in the expression there didn't occur the second derivative of this surface. So this story is begin with Cirolo and Maggi in 2017. They proved that in Euclidean space, hypersurfaces with delta 0 close to 0 must be close to the disjoint of unit ball boundary of unit balls, and by moving Plin's method, Cerullo and Veroni give another proof, and Cerullo and Veroni also research similar results in the hyperbolic space, and joint with Zancaroni, they give a uniform proof for space forms. On the other hand, some non-local version of mean curvature is also considered by Cerullo, Figani, Maggi, and Lovaga. Today, we focus on the following results by Delgadino, Maggi, Mihaela, and Neumayer. The special case, this case, they consider not the supercritical index delta 0. They consider the quantity delta 2 of omega, which means the mean curvature is close to a constant in the L2 scenes. The results goes like following. This is if a sequence of domains in the Euclidean space with normalized H0 equal to Bn, and if there exists a positive integer L and some positive small numbers sigma and kappa such that the diameter of the sequence of domains are uniformly bounded, and the area of the boundary of the sequence of domains are uniformly bounded by L times of the volume of the standard sphere with some error sigma. And they also assume the sequence of the boundary of the domains are uniformly mean convex, in the sense their mean curvature is uniformly bounded below by kappa times n. Under this assumptions, if the mean curvatures close to a constant in the L2 scenes, which means that 2 omega I goes to 0, then the sequence of domains will converge to a limit domain, which is the union of disjoint unit balls in the with the number of the balls smaller than the number L. And the convergence is in the sense that the volume of the difference of omega I and omega I is close to 0, and the area of the boundary of omega I is close to the area of the limit boundary is area. So this convergence, since they also deal with the collapsing case, the result here can only get some convergence not very strong. Another reason is because they only assume the weak assumption that the mean curvature is close to a constant in the L2 sense. So they also need some other condition, especially this uniformly mean convex condition. And we are thinking about whether these conditions are necessary. Here is some partial result. Our main result is like below, which says if the Warm energy of the surface is strictly smaller than 32 pi. Then when the mean curvature is close to its average in the L2 sense, we have the surfaces is homeomorphic to the sphere, which we call the topological rigidity. Also, since our condition are both scaling invariant, so we can normalize such that the area of the surface is equal to 4 pi, which is the area of the round sphere. With under this normalization, we have another parameterization of the image of this immersion surface, such that by the round sphere, such that under this parameterization, the pulling back metric of the surface is conformal to the metric of the round sphere, with the conformal factors very small. Moreover, we also have the immersion F bar is close to the standard embedding of the round sphere. So by this result, our sigma is close to the round sphere in a geometric way. So we call this result geometric rigidity. And there are some remarks for our results. First is the condition the mean curvature is close to the its average in the L2 sense is a condition similar to DMM delta 2 condition. In fact, if omega is a domain in three-dimensional Euclidean space with H0 normalized to be 2 and the area of the boundary is uniformly bounded by L times of the standard sphere, then after normalization such that the area of the surface equal to 4 pi, we have the mean curvature of the normalized surface is close to a constant in the sense it is smaller than delta 2 square, and moreover, we also have the Wilmer energy of the renormalized surface is a lot greater than 4 times 1 plus delta 2 square times the volume bound. So if we take L equals to 1, then we have the Wilmer energy strictly smaller than 32 pi. And our results are plus. And in this special case, we do not assume the uniformly bounded of the diameter, and we also do not need to assume the uniformly mean convex condition. Another remark is our condition on the Wilmer energy. In fact, 32 pi is just the Wilmer energy of two touched sphere. So we call this condition on the Wilmer energy the global non-collapsing condition. It is used to prevent the occurring of two or more touched spheres. It is also used to guarantee the immersion to be embedded. That is by Liao's inequality or Liang-Simons monotonicity formula. in fact, we have a more quantitative one, and this will finally guarantees our topological rigidity. We will explain this later. Moreover, we want to say that for sigma to be homeomorphic to a sphere, the condition on the Willmore energy is also necessary, since we have the counterexamples of Lawson's surfaces, which means the conformal deformation of Lawson's surfaces leads to a sequence of surfaces with two touched spheres as its limit, and the genesis were concentrated to a point. This means that there is a sequence of surfaces with mean curvature close to a constant in the L2 sense, but the topology of the surfaces are not sphere, and in fact the genesis can go to infinity. So the reason is because their Willmore energy is not uniformly smaller than 32 pi. In fact, as the genus goes to infinity, the surfaces degenerate, the Willmore energy is convergent to 32 pi. So the topological rigidity is very important for us. In fact, it is the key, the only difficult part for our result. In fact, if we know sigma is homeomorphic to a sphere, then by the Gauss-Bonnet formula, we have the L2 norm of the twist-free part of the second fundamental form is strictly less than 8 pi. An observation is that if the twist-free part of the second fundamental form is 0, then by Hopf differential and Koda's equation, the surface must have constant mean curvature. So, in principle, to establish quantitative rigidity for L2 almost constant mean curvature surface, we need first low quantitative rigidity for L2 almost total ambiguous surface, that is, for surfaces in Euclidean space with L2 integral of its twist-free part of second fundamental form very small. In fact, there is some known results on this direction. That is, Daninis and Milner, or Nam and Schatzner's quantitative rigidity for L2 almost ambiguous surface. Their result says if a surface is a topological sphere in the Euclidean space, and its area is normalized to be 4 pi, then if the L2 integral of the twist-free part of the second fundamental form is smaller than 2 times En, where En equals to 4 pi for n equals to 3. Then there exists a conformal parameterization f from the round sphere S2 to sigma such that the pulling back is a conformal metric with respect to the round sphere metric, and the conformal factor and the immersion itself will both be close to the standard one. So we note that in our case n equals to 3, the 2 times 4 pi is just 8 pi, which is exactly our are concluding from the topological rigidity and the Gauss split formula. So our key is to get the topological rigidity, that is sigma is close to that is sigma is homeomorphic to a sphere. This is in the next section.